In this video, we're going to have a look at how we can make the most of limited data using language, data augmentation strategies, and training approaches. More specifically, we're going to focus on something called Augmented SBERT. So you may or may not be aware that the past decade has been sort of a renaissance or explosion in the field of machine learning and data science. And a lot of that, especially the early progress with things like a perceptron and recurrent neural networks, a lot of that was researched and discovered back in the 50s and 60s and 70s. But we didn't see that really applied in industry or anywhere really until the past decade. And there are two main reasons for this. So the first is that we didn't have enough compute power back in the 50s, 60s, 70s to train the models that we needed to train. And we also didn't have the data to actually train those models. Now, compute power is not really a problem anymore. If we sort of look at this graph, it depends on what model you're training. Of course, if you are OpenAI and you're training GPT-4 or 5, whatever, yeah, maybe compute power is pretty relevant. But for most of us, we can get access to cloud machine or even our personal machines, and we can wait for a few hours or a couple of days and fine-tune or pre-train a transform model that is good performance or for what we need. Now, that obviously wasn't always the case until very recently. Back in 1960s, you see on this graph here, we have the IBM 704. And I mean, you can see on the y-axis, we have floating point operations per second. And that's a logarithmic scale. So a linear scale just basically looks like a straight line until a few years ago and then shoots up. It's pretty impressive how much progress is made in terms of computing power. Now, like I said, that's not really an issue for us anymore. We have the compute in most cases to do what we need to do. And data is not as much of a problem anymore, but we'll talk about that in a moment. So data, again, we have a very big increase in data, not quite as big as the computing power. And this graph here doesn't go quite as far back. It's only 2010, where I believe it was at 2 zettabytes, and now 71 or so in 2021. So there's a fairly big increase, not quite as much as computing power over time, but still pretty massive. Now, the thing with data is, yes, there's a lot of data out there, but is there that much data out there for what we need to train models to do? And in a lot of cases, yes, there is, but it really depends on what you're doing. If you are focusing on a more niche domain, so what I have here on the left over here are a couple of niche domains. There's not that much data out there on sentence pairs for climate evidence and claims, for example. So where you have a piece of evidence and a claim, and whether the claim supports evidence or not. There is a very small data set called climate fever data set, but it's not big. For agriculture, I assume within that industry there's not that much data, although I have never worked in that industry, so I'm not fully aware. I just assume there's probably not that much. And then also niche finance, which I do at least have a bit more experience with, and I imagine this is probably something that a lot of you will find useful as well, because finance is a big industry. There's a lot of finance data out there, but there's a lot of niche little projects and problems in finance where you find much less data. So yes, we have a lot more data nowadays, but we don't have enough for a lot of use cases. On the right here, we have a couple of examples of low resource data sets. So we have Dve from the Maldives and also the Navajo languages as well. So with these, we kind of need to find a different approach. Now, we can investigate, depending on your use case, unsupervised learning with TSDE, which we have covered in a previous video article. And that does work when you're trying to build a model that recognizes generic similarity, and it works very well as well. But for example, with the climate claims data, we are not necessarily trying to match sentence A and B based on their semantic similarity, but we're trying to match sentence A, which is a claim, to sentence B, which is evidence as to whether that evidence supports the claim or not. So in that case, unsupervised approach like TSE doesn't really work. So what we have is very little data, and there aren't really any alternative training approaches that we can use. So basically what we need to do is create more data. Now, data augmentation is difficult, particularly for language. So data augmentation is not specific to NLP. It's used across ML, and it's more established in the field of computer vision. And that makes sense because computer vision, you say you have an image, you can modify that image using a few different approaches, and a person can still look at that image and think, okay, that is the same image. It's just maybe it's rotated a little bit. We've changed the color grading, the brightness, or something along those lines. We've just modified it slightly, but it's still in essence the same image. Now, for language, it's a bit difficult because language is very abstract and nuanced. So if you start randomly changing certain words, the chances are you're going to produce something that doesn't make any sense. And when we're augmenting our data, we don't want to just throw rubbish into our model. We want something that makes sense. So there are some data augmentation techniques, and we'll have a look at a couple of the simpler ones now. So there is a library called NLP.org, which I think is very good for this sort of thing. It's essentially a library that allows us to do data augmentation for NLP. And what you can see here is two methods using word2vec, vectors and similarity. And what we're doing is taking this original sentence, so the quick brown fox jumps over the lazy dog, and we're just inserting some words using word2vec. So we're trying to find what words word2vec thinks could go in here, which words are the most similar to the surrounding words. And we have this Alziari, which I don't know, I think it seems like a name to me, but I'm not sure. That I don't think really fits there, so it's not great, it's not perfect. Lazy superintendent's dog, that does kind of make sense. I feel like a lazy superintendent's dog is maybe a stereotype, or I'm sure it's been in The Simpsons or something before. So okay, fair enough. I can see how that can fit in there, but again, it's a bit weird. It's not great. Substitution for me seems to work better. So rather than the quick brown fox, we have the easy brown fox, and rather than jumping over the lazy dog, jumps around the lazy dog, which changes the meaning slightly. Easy is a bit weird there, to be fair, but we still have a sentence that kind of makes sense. So that's good, I think. Now, we don't have to use word2vec. We can also use contextual word embeddings like with BERT. And for me, I think these results look better. So for insertion, we get even the quick brown fox usually jumps over the lazy dog. So we're adding some words there. It makes sense. That's, I think, good. Or substitution, and we're only doing one word here. And we're changing that to a little quick brown fox instead of just quick brown fox. So I think that makes sense, and this is a good way of augmenting your data and creating more data from less. But for us, because we are using sentence pairs, we can basically just take all of the data from say we have A and B over here. Imagine it's like a data frame, and we have all of these sentence A's, and we have all these sentence B's. Now, if we take one sentence A, it's already matched up to one sentence B. And what we can do is say, okay, I want to randomly sample some other sentence B's and match them up to our sentence A. So, we have 3 more pairs now. Okay, so if we did this, if we took 3 sentence A's, 3 sentence B's, and we made new pairs from all of them, so not really random sampling, but just taking all the possible pairs, we end up with 9 new or 9 pairs in total, which is much better. If you extend that a little further, so from just 1,000 pairs, we can end up with 1 million pairs. So you can see quite quickly we can take a small data set and very quickly create a big data set with it. Now, this is just one part of the problem though, because our smaller data set will have similarity scores or natural language inference labels, but the new data set that we've just created, the augmented data set, doesn't have any of those. We just randomly sample new sentence pairs, so there's no scores or labels there, and we need those to actually train a model. So what we can do is take a slightly different approach, or add another step into here. Now, that other step is using something called a cross encoder. So in semantic similarity, we can use 2 different types of models. We can use a cross encoder, which is over here, or we can use a bi-encoder, or what I would usually call a sentence transformer. Now, a cross encoder is the sort of old way of doing it, and it works by simply putting sentence A and sentence B into a BERT model together at once. So we have sentence A, separator token, sentence B, feed that into a BERT model, and from that BERT model we will get all of our sort of embeddings, output embeddings over here, and they all get fed into a linear layer, which converts all of those into a similarity score up here. Now, that similarity score is typically going to be more accurate than a similarity score that you could get from a bi-encoder or sentence transformer. But the problem here is, from our sentence transformer, we are outputting sentence vectors. And if we have 2 sentence vectors, we can perform a cosine similarity or Euclidean distance calculation to get the similarity of those 2 vectors. And the cosine similarity calculation or operation is much quicker than a full BERT inference set, right? Which is what we need with a cross encoder. So I think it is something like, for maybe clustering 10,000 vectors using a cross encoder, an SBERT cross encoder, would take you something like 65 hours, whereas with a bi-encoder, it's going to take you about 5 seconds. So it's much quicker. And that's why we use bi-encoders or sentence transformers. Now, the reason I'm talking about cross encoders is because we get this more accurate similarity score, which we can use as a label. And another very key thing here is that we need less data to train a cross encoder. With a bi-encoder, I think the SBERT model itself was trained on something like 1 million sentence pairs. and some newer models are trained on like 1 billion or more. Whereas a cross-encoder, we can train a reasonable cross-encoder on something like 5K or maybe even less sentence pairs. So we need much less data, and that works quite well what we've been talking about with the data augmentation. We can take a small data set, we can augment it to create more sentence pairs, and then what we do is train on that original data set, which we call the gold data set. We train our cross-encoder using that, and then we use that fine-tuned cross-encoder to label the augmented data set without labels, and that creates a augmented labeled data set that we call the silver data set. So that sort of strategy of creating a silver data set, which we would then use to fine-tune our bioencoder model, is what we refer to as the in-domain Augmented SBERT training strategy. Okay, and this sort of what you can see, this flow diagram, is basically every step that we would need to do to create an in-domain or SBERT training process. So we've already described most of this. So we get our gold data set, the original data set. That's going to be quite small. Let's say 1 to 5,000 sentence pairs that are labeled. From that, we're going to use something like random sampling, which I'll just call rand samp. We're going to use that to create a larger data set. Let's say we create something like 100,000 sentence pairs, but these are not labeled. We don't have any similarity scores or natural language inference labels for these. So what we do is we take that gold data set and we take it down here and we fine tune a cross encoder using that gold data, because we need less data to train a reasonably good cross encoder. So we take that and we fine tune cross encoder, and then we use that cross encoder alongside our unlabeled data set to create a new silver data set. Now, the cross encoder is going to predict the similarity scores or NLI labels for every pair in that data set. So with that, we have our silver data. We also have the gold data, which is up here. And we actually take both of those together and we fine tune the bioencoder or the sentence transformer on both the gold data and the silver data. Now, one thing I would say here is it's useful to separate some of your gold data at the very start, so don't even train your cross encoder on those. It's good to separate them as your evaluation or test set, and evaluate both the cross encoder performance and also your bioencoder performance on that separated set. So don't include that in your training data for any of your models. Keep that separate, and then you can use that to figure out, is this working or is it not working? So that is in-domain augmented SBERT, and you sort of see this is the same as what you saw before, just this is the training approach. So we have the gold trained cross encoder. We have our unlabeled pairs, which would come from random sampling our gold data. We process those through our cross encoder to create a silver data set. And then the silver and the gold come over here to fine tune a bioencoder. So that's it for the theory and the concepts. And now what I want to do is actually go through the code and we'll work through an example of how we can actually do this. Okay, so we have downloaded both the training and the validation set for our STSB data. And let's have a look at what some of that data looks like. So STSB 0. So we have sentence pair, sentence 1, sentence 2, just a simple sentence. And we have a label, which is our similarity score. Now, that similarity score varies from between 0 up to 5, where 0 is no similarity, no relation between the two sentence pairs, and 5 is they mean the exact same thing. Now, see here, these two mean the same thing as we. Now we can see here that these two mean the same thing as we would expect. So we first want to modify that score a little bit, because we are going to be training using cosine similarity loss, and we would expect our label to not go up to a value of 5, but instead go up to a value of 1. So all I'm doing here is changing that score so that we are dividing everything by 5, or normalizing everything. So we do that, and no problem. And now what we can do is load our training data into a data loader. So to do that, we first format everything into a input example, and then load that into our PyTorch data loader. So I'll run that, and then at the same time during training, I also want to output a evaluation score. So how did the cross-encoder do on the evaluation data? So to do that, I import. So here we're importing from sentence transformers cross-encoder evaluation. I'm importing the cross-encoder CE correlation evaluator. I'm using input examples. We're working with sentence transformers library, and I am importing both text and the labels. And here I am putting all of that development, or I'm putting all of that validation or dev data into that evaluator. Okay, and I can run that. And then we can move on to initializing a cross-encoder and training it and also evaluating it. So to do that, we're going to import from sentence transformers. So from sentence transformers, and I'll just make sure I'm working in Python. I'm going to import from cross-encoder a cross-encoder. Okay, and to initialize that cross-encoder model, I'll call it C. All I need to do is write cross-encoder, very similar to when we write sentence transformer and initialize a model. We specify the model from Hugging Face transformers that we like to initialize a cross-encoder from, so BERT, base, and case, and also the number of labels that we'd like to use. So in this case, we are just targeting a similarity score between 0 and 1. So we just want a single label there. If we were doing, for example, NLI labels where we have entailment, contradiction, and neutral labels, or some other labels, we would change this to, for example, 3. But in this case, 1, we can initialize our cross-encoder. And then from there, we move on to actually training. So we call model or ce.fit, and we want to specify the data loader. So this is slightly different to the fit function we would usually use with sentence transformers. So we want train data loader. We specify our loader that we initialize just up here, the data loader. We don't need to do this, but if you are going to evaluate your model during training, you also want to add in evaluator as well. So this is from the CE correlation evaluator. Make sure here you're using a cross-encoder evaluation class. We would like to run for, say, 1 epoch, and we should define this because I would also like to, while we're training, I would also like to include some warm-up sets as well, which I'm going to include a lot of warm-up sets actually, although, well, I'll mention it, I'll talk about it in a moment. So I would say number of epochs is equal to 1. And for the warm-up, I would like to take integer, so the length of loader, so the number of batches that we have in our data set. I'm going to multiply this by 0.4. So I'm going to do a warm-up or do warm-up sets for 40% of our total data set size or batch, or 40% of our total number of batches. And we also need to multiply that by number of epochs. Say if we're training 2 epochs, we would multiply that. In this case, just 1. So not necessary, but it's there. So we're actually performing warm-up for 40% of the training steps, and I found this works better than something like 10%, 15%, 20%. However, that being said, I think you could also achieve a similar result by just decreasing the learning rate of your model. So by default, so if I write num epochs here, we'll define the warm-up sets equals warm-up. So by default, this we use optimizer params with a learning rate of 2e to the minus 5. Okay, so if you say wanted to decrease that a little bit, you could go, let's say, go to the minus 6, 5e to the minus 6. And this would probably have a similar effect to having such a significant number of warm-up steps. And then in this case, you could decrease this to 1 or 10%. But for me, the way I've tested this, I've ended up going with 40% warm-up steps, and that works quite well. So the final step here is, where do we want to save our model? So I'm going to say I want to save it into BERT base cross encoder. Or let's say BERT STSB cross encoder. And we can run that, and that will run everything for us. I'll just make sure it's actually, yep, there we go. So see it's running, but I'm not going to run it because I've already done it. So let me pause that, and I will move on to the next step. Okay, so we now have our gold data set, which we have pulled from Hugging Face datasets, and we've just fine-tuned a cross encoder. So let's cross both of those off of here, this and this. And now, so before we actually go on to predicting labels with the cross encoder, we need to actually create that unlabeled data set. So let's do that through random sampling using the gold data set we already have, and then we can move on to the next steps. Okay, so I'll just add a little bit of separation in here. So now we're going to go ahead and create the augmented data. So as I said, we're going to be using random sampling for that. And I find that the easiest way to do that is to actually go ahead and use a pandas data frame rather than using the Hugging Face dataset object that we currently have. So I'm going to go ahead and initialize that. So we have our gold data. That will be pd.dataframe. And in here, we're going to have sentence 1 and sentence 2. So sentence 1. That is going to be equal to STSB sentence 1. Okay, and as well as that, we also have sentence 2, which is going to be STSB sentence 2. Now, we may also want to include our label in there, although I wouldn't say this is really necessary. we'll add it in. So our label is just label. And if I have a look here, so we have, so I'm going to overwrite anything called gold. It's okay. So, okay, and we can have a look at that as well, so we can see a few examples of what we're actually working with. I'll just go ahead and actually rerun these as well. Okay, so there we go. We have our gold data, and now what we can do, because we've reformatted that into a pandas data frame, we can use the sample method to randomly sample different sentences. So to do that, what I will want to do is create a new data frame. So this is going to be our unlabeled silver data set. It's not a silver data set yet because we don't have the labels or scores yet, but this is going to be where we will put them. And in here, we again will have sentence 1 and also sentence 2, but at the moment they're empty. There's nothing in there yet. So what we need to do is actually iterate through all of the rows in here. So before that, I'm just going to do from or import tqdm.auto from tqdm auto import tqdm. And that's just a progress bar, so we can see, where we are. I don't really like to wait and have no idea how long this is taking to process. And for sentence 1 in tqdm, so we have the progress bar, and I want to take a list of a set, so we're taking all the unique values in the gold data frame for sentence 1. Okay, so that will just loop through every single unique sentence 1 item in there, and I'm going to use that, and I'm going to randomly sample 5 sentences from the other column, sentence 2, to be paired with that sentence 1. And here our sample, or the sentence 2 phrases that we're going to sample are going to come from the gold data, of course. And we only want to sample from rows where sentence 1 is not equal to the current sentence 1, because otherwise we are possibly going to introduce duplicates. And we're going to remove duplicates anyway, but let's just remove them from the sampling in the first place. So we're going to take that, so all of the gold data set that where sentence 1 is not equal to sentence 1, and what I'm going to do is just sample 5 of those rows like that. Now from that, I'm just going to extract sentence 2, so the 5 sentence 2 phrases that we have there, and I'm going to convert them into a list. And now for sentence 2 in the sampled list that we've just created, I'm going to take my pairs and I'm going to append new pairs. So pairs.append, and I want sentence 1 to be sentence 1, and also sentence 2 is going to be equal to sentence 2. Now this will take a little while, so what I'm going to do is actually maybe not include the full data set here. So let me possibly just go maybe the first 500. Yeah, let's go to first 500, see how long that takes. And I will also want to just have a look at what we get from that. Okay, so yes, it's much quicker. Okay, so we have sentence 1. Let me remove that from there. And let's just take the top 10, right? So because we're taking 5 of sentence 1 every time and random sampling it, we can see that we have a few of those. And another thing that we might want to do is remove any duplicates. Now, there probably isn't any duplicates here, but we can check. So pairs equals pairs.drop duplicates, and then we'll check the length of pairs again. Okay. Also print. Let me run this again and print. Okay, so there were not any duplicates anyway, but it's a good idea to add that in just in case. And now what I want to do is actually take the cross encoder. In fact, actually, let's go back to our little flow chart. So we have now created our larger unlabeled data set. So it's good. And now we go on to predicting the labels with our cross encoder. So down here, what I'm going to do is take the cross encoder code here. And what I've done is I've trained this already and I've uploaded it to the Hugging Face models. So what you can do and what I can do is this. So I'm going to write James Callum, and it is called BERT STSB cross encoder. Okay. Okay, so that's our cross encoder. And now what I want to do is use that cross encoder to create our labels. So that will create our silver data set. Now to do that, I'm going to call it silver for now. I mean, this isn't really the silver data set, but it's fine. And what I'm going to do is create a list, and I'm going to zip both of the columns from our pairs. So pairs sentence 1, pairs sentence 2, pairs sentence 1, and pairs sentence 2. Okay, so that will give us all of our pairs again. You can look at those. Okay, so it's just like this. And what we want to do now is actually create our scores. So we just take the cross encoder. What did we load it as? ce.predict, and we just pass in that silver data. So we do that. Let's run it. It might take a moment. Okay, so it's definitely taking a moment. So let me pause it. I'm going to just do, let's say 10, because I already have the full data set, so I can show you that somewhere else. And let's have a look at what we have in those scores. So 3 of them. So we have an array, and we have these scores. Okay, so that they are our predictions, our similarity predictions for the first 3. Now, because they're randomly sampled, a lot of these are negative. So if we go silver, say negative, I mean more, they're not relevant. So yeah, we can see not particularly relevant. And that's just one, I suppose, issue with this. And you can change, you can try and modify that by, after creating your scores, if you oversample and score a lot of values or a lot of records, and then just go ahead and remove most of the low scoring samples and keep all of your high scoring samples, that will help you deal with that imbalance in your data. So what I'm going to do is I'm going to add to the labels column those scores, which will not actually cover all of them because we only have 10 in here. So let me maybe multiply that. So this isn't, you shouldn't do this, obviously. It's just so they fit. Okay, and let's have a look. Okay, so we now have sentence 1, sentence 2, and some labels. And what you do, although I'm not going to run this, is you would write pairs.toCSV, Don't necessarily need to do this if you're running everything in the same notebook, but that's probably a good idea. Silver TSV, so I'm going to save the silver data as a tab separated file, and obviously the separator for that type of file is a tab character, and I don't want to include an index. Okay, and that will create the silver data file that we can train with, which I do already have. So if we come over here, we can see that I have this file, and we have all of these different sentence pairs and the scores that our encoder has assigned to them. So I'm going to close that, and I'm going to go back to the demo. And what I'm now going to do is actually, well, first go back to the flow chart that we had. I'm going to cross off predict labels, and we're going to go ahead and fine tune the bioencoder on both gold and silver data. So we have the gold data. Let's have a look at what we have. Yes, and the silver, I'm going to load that from file. So pd.read csv, silver.tsv. Separator is a tab character, and let's have a look at what we have. Make sure it's all loaded correctly. Looks good. Now what I'm going to do is put both those together. So all data is equal to gold.append silver, and we ignore the index, so we don't get an index error. Sorry, true. And all data.head. Okay, we can see that we hopefully now have all of the data in there. So let's check the length. Yeah, so it's definitely a bigger data set now than before with just gold. Okay, so we now have a larger data set, and we can go ahead and use that to fine tune the bioencoder or sentence transformer. So what I'm going to do is take the code from up here. So we have this train data, and I think I've already run this before, so I don't need to import the input example here. But what I want to do here is for row in all data, and what we actually want to do here is for I row in all data, because this is a data frame. We want iteros, so iterate through each row. We have row, sentence 1, sentence 2, and also a label. So we load them into our train data, and we can have a look at that train data, see what it looks like. Again, we see that we get all these input example objects. If you want to see what one of those has inside, you can access the text like this. Should probably do that in a new cell. So let me pull this down here, and you can also access a label to see what we have in there. Okay, so that looks good, and we can now take that like we did before and load it into a data loader. So let me go up again, and we'll copy that. Where are you? Take this, bring it down here, and we run this. Creates our data loader, and we can move on to actually initializing the sentence transformer or bioencoder and actually training it. So we want to run from sentence transformers. We're going to import models, and we're also going to import sentence transformer. Now, to initialize our sentence transformer, if you've been following along with the series of videos and articles, you will know that we do something It looks like this. So we're going to call BERT, and that is going to be models.transformer. And here we're just loading a model from Hugging Face transformers, so BERT based on case. And we also have our pooling layer. So models again, and we have pooling. And in here, we want to include the dimensionality of the vectors that the pooling layer should expect, which is just going to be BERT.get word embedding dimension. And also, it needs to know what type of pooling we're going to use. Are we going to use CLS pooling? Are we going to use mean pooling, max pooling, or so on? Now, we are going to use pooling, and we're going to use a mean. So mode mean tokens. Let me set that to true. So they're the two, let's say, components in our sentence transformer, and we need to now put those together. So we're going to call model equals sentence transformer, and we write modules, and then we just pass as a list BERT and also pooling. Okay. So we run that. We can also have a look at what our model looks like. Okay, and we have, you see, we have a sentence transformer object, and inside there we have two layers or components. First one is our transformer, it's a BERT model, and the second one is our pooling. And we can see here the only pooling method that is set to true is the mode mean tokens, which means we're going to take the mean across all of the word embeddings output by BERT and use that to create our sentence embedding or vector. So with that model now defined, we can initialize our loss function. So we do want to write from sentence transformers dot losses import cosine similarity loss. So cosine similarity loss, and in here we need to pass the model so it understands which parameters to actually optimize, and initialize that. And then we set up our training function, or the fit function, and that's similar to before, the cross encoder, although slightly different. So let me take that. It's a little further up from here. I'm going to take that and we're just going to modify it. So warm up, I'm going to warm up for 15% of the number of steps that we're going to run through. We change this to model because it's not C anymore. And like I said, there are some differences here. So we have a training objectives, that's different. And this is just a list of all the different training objectives we are only using one, and we just pass the loader and loss into there. Evaluator, we could use an evaluator. I'm not going to. For this one, I'm going to evaluate everything afterwards. The epochs and warm steps are the same. The only thing that's different is the output path, which is going to be BERT STSB org. That's it. So go ahead and run that. It should run. Let's check that it does. Okay, so I've got this error here, so it's lucky that we checked. And we got this runtime error found D-type long but expected float. And if we come up here, it's going to be in the data loader or in the data that we've initialized. So so here I've put int. For some reason, I'm not sure why I did that. So this should be a float, the label in your training data. And that should be the same up here as well. Okay, so here as well, the cross encoder, we would expect a float value. So just be aware that I'll make sure there's a note in the video earlier on for that. Okay, and okay, let's continue through that and try and rerun it. It should be okay now. Oh, I need to actually rerun everything else as well. So rerun this. Okay, label 1.0. Okay, it's better. This. Okay, I'll just leave this for a moment just to be sure that it is actually running this time, but it does look good. So yeah, that's fine. So it looks good. When for some reason in the notebook, I'm actually seeing the number of iterations, but okay, I've paused it now and we can see that yes, it did run through 2 iterations, so it is running correctly now. That's good. So that's great. What I want to do now is actually show you, okay, evaluation of these models. So back to our flowchart quickly. Okay, so fine-tune by Encoder. We've just done it. So we've now finished with our in the main Augmented SBERT training strategy. And yeah, let's move on to the evaluation. Okay, so my evaluation script here is maybe not the easiest to read. But basically all we're doing is we're importing the embedding similarity evaluator from down here. I'm loading the glue data, STSB again, and we're taking the validation split, which we didn't train on. We are converting that into input examples, feeding it into our embedding similarity evaluator, and loading the model. The model name I've passed through command line arguments from up here, and then it just prints out the score. So let me switch across to the command line. We can see how that actually performs. Okay, so just switch across to my other desktop because this is much faster, so I can actually run this quickly. So Python 03, so we're going to run that evaluation script. And what we're going to pass here is we have all three, the cross encoder, the sentence transformer trained using Augmented SBERT, and also a sentence transformer trained purely on the gold dataset. So first, let's have a look at the BERT STSB gold dataset trained model. So run this. It might take a moment to download it. Okay, so everything downloaded, and then we got a score of 0.506. So it correlates to the predictions of the model correlate to the actual scores with a sort of 50% correlation. So they do correlate. It's not bad. It's not great either. Let's have a look at the cross encoder. So again, cross encoder. Okay, and we get a score of 0.58. So as we would expect, training on just the gold data, the cross encoder does outperform the bi-encoder or sentence transformer. And the final one would be, okay, with the augmented data, how does the sentence transformer perform? So let's run that again. We'll have to wait for it to download. And we get a much better score of 0.69. So yeah, the correlation there is much higher than this for the augmented data set than if we had just used a gold data set. So it really has improved the performance a lot. Now this is maybe an atypical performance increase. It's like 90% or 19 point increase in performance, and that's good. But if you look at the original paper from Nils Reimers and co, they found a sort of expected performance increase of, I believe, 7 or 9 points. So this is definitely pretty significant. This is definitely a bit more than that, but I think it goes to show how good these models or this training strategy can actually be. So that's it for this video. I hope this has been useful, and I hope this helps a few of you kind of overcome the sometimes lack of data that we find in I think, a lot of our particular use cases. Thank you very much for watching, and I will see you in the next one.